Hello everyone, and welcome to another tutorial on Fourier Series. In the last tutorial for Fourier Series, we looked at what periodic functions are, looked at Fourier Series, looked at useful integrals, we also looked at dirichlet conditions, and finally, we took a simple example to illustrate how Fourier Series work. In this tutorial, we will continue from where we stopped by looking at functions that are defined in 12 ranges. We also look at even and odd functions, and lastly, half-range functions. The last example I gave was f of x equal to x for 0 less than x less than pi. Now, this function has a single range, which is from 0 to pi. So now let's see a new function. Our f of x now is equal to a piecewise function where it has a value minus pi over 4 for minus pi less than 0. Oh, sorry, it should be less than x less than 0, and a value pi over 4 for 0 less than x less than pi. So how do we find the Fourier series for this kind of a function? Well, still a very similar step like we took before. The first thing here is to identify the period. Now, despite the fact that our f of x has two ranges, which is minus pi to 0 and 0 to pi, the period for f of x is still going from minus pi to pi, which makes it 2 pi. So our period for integrating is still what? 2 pi. So with this, we can find our a naught, we can find our bn, and our an. So for a reminder, a naught is equal to 1 over the period. Integral 0 to 2 pi. Well, this could change depending on the range you're given. For example, if I'm using this here, this means 0 to 2 pi again. It will become what now? Minus pi to 0. And for it to become 0 to pi. But the period stays as what? 2 pi. Because the 2 pi here is for the entire function f of x. Are we clear on that? Very good. So our a naught is equal to 1 over period, integrating from 0 to 2 pi, f of x dx. Our an is equal to 1 over half of the period, 0 to 2 pi, f of x cos nx dx. I think I also visited integration by parts in the last tutorial to explain how to solve some questions, or how to solve some integration questions that can only be solved by parts. And lastly, our bn is equal to 1 over the period over 2, going from 0 to 2 pi, or the range we're giving, f of x sine nx dx. So please take note of these things. Take note of those formulas. So let's quickly continue the question. So now let's find out a naught. A naught equal to 1 over, what's the period? 2 pi. Integrating from what? Now we'll have two separate integrations. So we'll have what now? Minus pi over 4, going from minus pi to 0 dx. And also we would have 1 over 2 pi from 0 to pi of what? Pi over 4 dx. So let's work around this integration. It should be very easy. So we have a naught equal to 1 over 2 pi going from minus pi to 0, and this will give us minus pi over 4x. And also we would have 1 over 2 pi going from 0 to pi over 4x. So substituting the values of x, 0 and minus pi, and 0 and pi, what do we have? And one thing we can do here, let's factorize our 1 over 2 pi out. So we have 1 over 2 pi. This is a constant. and now have minus pi. Now we can even factorize our pi over 4 out. That should make it further simpler. So let me erase this. So this gives us 1 over 2 pi times pi over 4. So we're left with minus x from minus pi to 0 plus x 0 to pi. Okay, let me rub the bar off. Okay, I hope you guys have taken note of the question. I hope you have taken note of the question. So moving forward, we should have a naught equal to pi cancels the pi here, so you're left with 1 over 8. So our minus x is from 0 to minus pi. Sorry, minus pi to 0. So we should have this minus 0 minus into minus pi. I hope that's clear. Plus pi minus 0. So let's see what this gives us. Let's go by it again. We have 0, so minus 0, then minus x, making it minus into minus pi. So we need to be very careful with this outside. So this gives us 1 over 8 minus 0 minus here becomes plus, times minus we get minus. So in total we have minus pi plus pi, which is 0. So it means our a naught here equal to 0. Up next, let's find our an. The formula again, an is equal to 1 over the period over 2, integrating 0 to 2 pi of the given range, f of x cos nx dx. So let's go. And remember that our period is 2 pi. So we'll have a piecewise integration. So an is equal to 1 over 2 pi. Or 1 over 2 pi? No. 1 over 2 pi over 2, which is still 1 over pi. So we have this 1 over pi. Going from minus pi to 0 of minus pi over 4. I hope you can see my pi. I'm not so good at writing pi. Minus pi over 4 cos nx dx plus 1 over pi, going from 0 to pi over 4 cos nx dx. So just like we did in the last integration for a naught, let's factorize the constant out. So 1 over pi is common, pi over 4 is common. So let me just write this. That will give us 1 over 4. So we have 1 over 4 outside, integrating from minus pi to 0 cos nx dx, and we still have a minus here, plus integrating 0 to pi of cos nx dx. So quickly, integral of cos nx dx, what does that give us? That gives us sine nx all over n. So this leads us to this 1 over 4. We have our range minus pi to 0 minus sine nx over n plus 0 to pi sine nx all over n. So times plug now values. You need a bigger delta to rub this word faster. Okay, so from here we have an is equal to 1 over 4. Okay, let's plug now value. So we have 0 first here. That's minus sine n 0 over n minus sine n minus pi all over n for the first part, plus sine n pi, put in the pi, this pi here, over n minus sine n 0 all over n. Now remember from the last tutorial that I said sine n pi equals 0. So we have 1 over 4 sine n 0, which is sine 0, is 0. We have sine n pi 0, sine n pi 0, sine n 0, which is sine 0, that is 0. So everything here is 0. So an is equal to 0. So now let's find our bn. Formula for bn is equal to 1 over half of the period, going from 0 to 2 pi, or the range given to us, f of x sine nx dx. So I'm just going to clean this. So we have bn is equal to 1 over pi, because our period was 2 pi. 1 over pi, going from minus pi to 0, or minus pi over 4 dx, plus 1 over pi, 0 to pi, pi over 4 dx. So let's simplify the expression. Let's factor out 1 over pi and pi over 4 again. And that would lead us to 1 over pi outside times pi over 4, giving us 1 over 4. So we have 1 over 4 minus pi to 0 minus, oh, we forgot to put our sine x dx. Let's add that here. Sine nx dx. My bad. Sine nx dx. Alright, let's continue. So we have sine nx dx plus 0 to pi sine nx dx. So integrating sine x, we get minus cos x. So integrating minus sine nx, we get minus cos nx over n. Let me say that again. Integrating sine x, we get minus cos x. But now, integrating sine nx, we get minus cos nx all over n. So we have this. Bn is equal to 1 over 4, going from minus pi to 0. Now, because we're already having a minus here, it cancels out the minus from the integration. So this gives us cos nx over n, then plus minus cos nx. Oh, let me just factor out the negative sign. So this gives us minus, going from 0 to pi. So now let's plug in our limits. So we have 1 over 4. 1 over 4, so we have cos n0 over n minus cos n minus pi all over n. And then let's come here. We have cos n pi over n. Now, because we're already having a minus here, by the time you expand it, you should have plus here. So you have cos n0 all over n. So let's check. Cos n0 is still cos 0, and that's 1. Cos n minus pi so from here, okay, let me clean the board. Some space. So we have 1 over 4. Cos n0 is still cos 0, and cos 0 is 1. We have 1 over here. Cos n minus pi, or cos minus n pi, is same thing as cos n pi, because cos is an even function. Cos x is equal to cos minus x. So please note that. And remember from the last tutorial that I said, cos n pi is equal to minus 1 raised to power n. So what we have here is minus 1 raised to power n all over n. That's for this. Cos n pi here, same thing. We have minus 1 raised to power n all over n. And we have cos n0, which is still cos 0, all over n. So we have 1 over n. So we can now wipe this off. So from here, our Bn is equal to 1 over 4. We have 1 plus 1 over n plus 1 over n. That should give us 2 over n. We have minus 1 raised to power n over n, and the same thing here. So we have this minus 2 into bracket minus 1 raised to power n all over n. So we can say that n is common and 2 is common. So let's factor out 2 and n. We have 2 over n times 1 over 4. Then we have 1 minus 1 raised to power n. So 2 here, 1, we have 2 here. So Bn now is equal to 1 over 2n. 1 minus 1 raised to power n. Now, Bn, it has an expression that depends on what n is. So we have to check. For odd values of n, what is our Bn? And for even values of n, what is our Bn? So let's check. So when n is odd, for odd n, our Bn will be equal to 1 over 2n, 1 minus. So we know that minus 1 is our odd number, so it gives us minus 1. So we still have minus 1, giving us 1 over 2n, 1 plus 1, which is 2, and giving us 1 over n. Now let's check. When n is even, our Bn becomes 1 over 2n, and we know that minus 1 raised to power an even number will give us 1. So we have 1 minus 1, giving us 0. So this tells us that the Bn only exists for odd values of n. So to recap, from what we have solved so far, our A0 is equal to 0, our An is also equal to 0, and our Bn finally is equal to 1 over n only for odd values of n. So recall that Fourier series takes a periodic function f of x and expresses it in terms of its component, which is A0, plus summation as n goes from 1 to infinity of an cos nx, plus summation as n goes from 1 to infinity of bn sin nx. And our A0 here is 0, our an here is 0, so we only have the values for bn, only for odd values of n. So our f of x equal to n equal to odd, to show that it only works for odd values of n, up to infinity. And what's our bn? 1 over n. Let's factor that out here. Sin nx. So this is one way to write our answer. Another way to write our answer is to expand it. So this could also be written as f of x is equal to, so let's go odd values. We have 1 over 1 sin x. So we have sin x plus sine 3x over 3 as 1 over 3 times sine 3x. Then you can have sine 5x over 5. And we can keep going up to what? Infinity. So I hope that's clear. So let's look at even functions. Now, Fourier series aside, what are even functions? These are functions that are equal for both positive and negative value of the dependence variable, or I mean the independence variable, which is mostly x. So let's say we have f of x equal to x squared. Of course, we know that x is the independence variable and f of x is the dependence variable. So if f of x is equal to x squared, and by changing my x to minus x, I still get the same thing as f of x. This tells me that f of x is an even function. So to sum up, we can just say that f of x is an even function if f of x is equal to f minus x. And f minus x here simply means substituting the value of x with minus x in the expression. Another thing to know about even function is how the graph looks like. A typical graph for an even function would look like this. This is the graph of cos x. So what can we notice from this graph? We can see that from this graph, the function is symmetric about the y-axis. So if I have minus pi and I have pi here, we can say that the area under this curve is the same thing as double the area on this curve. That's not something to note. Therefore, is a symmetric function or an even function, the area under the curve, well, if the curve is periodic, is same thing as doubling the area under the positive axis. So having understood this, let's go back to Fourier series. Now for an even function, what is our a naught, what is our bn, and what is our an? Recall that a naught is equal to 1 over the period going from 0 to 2 pi f of x dx. Now, like I've been saying, the 0 to 2 pi here could change depending on what range we are given. So this is not static. So now our period, for this function itself, we have minus pi to pi, which means we can decide to do minus pi to what here? To pi. And before I proceed, because it's going from minus pi to pi, so first of all, we should even know that the period is actually what? 2 pi. That's pi minus minus pi. So I could write this as this 1 over 2 pi going from minus pi to pi f of x dx. But because I know that this is an even function, and I know that for an even function, the area under the entire curve, as for both positive and negative axis, is the same as doubling the area on the positive axis. So I can rewrite this as this 1 over 2 pi 2 times the area, which is 0 to pi, of this. I hope this is clear now. Now we have 1 over 2 pi, or 2 over 2 pi, which is still 1 over pi, going from 0 to 2 pi of f of x dx. So take note of this for your even functions. Okay, now our AN, similarly to our A naught, our AN is usually 1 over the period over 2, going from 0 to 2 pi f of x cos nx dx. Now, by default, cos x is even. And our f of x here for this scenario is also even. So an even function multiplied an even function still gives us an even function. And like we did here, we have 1 over pi. We have a naught is equal to 1 over pi. But let's check properly. 1 over the period over 2. What's our period? 2 pi. That's 1 over pi. Times 2 of the area on the positive axis, like I explained earlier. 0 to pi f of x dx. So from here, our an is equal to 2 over pi instead, from 0 to pi f of x dx. And lastly, our bn. Our bn is usually 1 over the period of 2, going from 0 to 2 pi f of x sine nx dx. Now, sine x is not an even function. Now, let me show you why. If you have sine theta, it is not equal to sine negative of theta. Rather, it is equal to minus sine theta. So this tells us that sine is an odd function which is skew symmetric, and we will get to that very soon. So multiplying an even function by an odd function gives us an odd function, which means that for an even function, we have no harmonics for Bn. So our Bn is 0. So whenever we have a question and we have to find the Fourier series. To save our time, we can first of all check if the function is even or odd. So if it happens that our function is even, we only need to find our a naught and an using the formula I gave you, and your bn is automatically equal to 0. So I hope you guys got that right. So let's look at odd function now. For an odd function, our f of x is equal to negative of our f minus x. I think that's a better way to put it. And our odd function is not symmetric about the y-axis. It is skew symmetric. And to save our time, let's look at the expansion of the Fourier series for an odd function. Let me give you a simple odd function example first before we proceed. So let's say we have f of x equal to x cubed. Now, when we try to get f of minus x, we have minus x all raised to power 3, which is equal to minus x cubed. And remember that x cubed itself is f of x. So this is equal to minus f of x. So I hope this is clear now. So with this information, let's see the expansion of the Fourier series for an odd function. Our a naught so for our a naught is 0 for an odd function. But let me show you why. Let's take a graph of sine x. So the basic idea of a naught is area on the curve. So we will notice from here that the area under the curve for this section is negative of the area under the curve for this axis, which means if my area here is 40, my area here will be minus 40. Unlike the one for even function, where the area here and the area here are equal. So it means they can overlap to give us 80. But this time around, the area here and area here are negative of each other. So basically, minus 40 plus 40 will give me 0. So that means our A naught here is 0. So if you have a function that is odd, and if you have to find the Fourier series, don't bother looking for the A naught, because it's equal to what? 0. Let's go to our AN. Our AN is equal to 1 over period over 2, going from 0 to 2 pi over f of x, which is an odd function now. Cos nx dx. Now what happens here? So our A of n here, we have f of x, which is an odd function multiplying an even function. So what do we get? We get an odd function, which makes our an also 0. And for our bn equals to 1 over p over 2, going from 0 to 2 pi, f of x sine n of x dx. Now, our f of x here, like I've been saying, is an odd function. Sine nx here is also an odd function. And an odd function multiplying another odd function gives us an even function. So just like our an for the even function was 2 over pi, going from 0 to pi, f of x cos nx dx. Our b of n for the odd function also equals to 2 over pi, going from 0 to pi, f of x sine nx dx. So that's all for today, guys. We have looked at functions defined in subranges. We have looked at even functions. We have looked at odd functions. So before I end the class, let me give you a question to try on your own. I have two questions. So try this. So this will test your knowledge of getting Fourier series for an even function and an odd function. So number one, obtain the Fourier series for f of x equal to x cubed for minus pi less than x less than pi. And number two, f of x equal to x squared for minus pi less than x less than pi. So that's all, guys. Catch you guys in the next tutorial.